So the training finished overnight, and in this tutorial, I want to show you how you can integrate the inference service into your robot program. But first of all, let's check the quality of the training result, and to do so, let's put a few of the workpieces we have here under the camera. But before we get started, please make sure that the inference app, Plane Picking, is installed on the edge device named Tutorials. The other thing we need to do in preparation is create a so-called grip, and I will just briefly explain what that means and how to do it. Now remember that the plane picking service is intended for precise assembly or precise placement of the workpiece inside a machine. That means that at pick time, the gripper needs to have a well-defined pose relative to the object. That definition, of course, can be done purely virtually, so at hand of the digital 3D CAD model of the object. So let's go ahead and open our product again and click on Add Grips. We'll see another dialog pop up in which we can add our first grip. So obviously you get to find more than a single grip, and the reason for that is pretty simple. At runtime, the first grip could be blocked either by the wall of a box or other pieces laying around. So what our service will do is we'll check one after another all the grips that we define here, and we'll return the first collision-free one to the robot. So what we can do is position the gripper model relative to the CAD model of the object using these buttons here. Pretty similar to jogging a robot relative to its current tool frame. So here we see a visualization of that TCP coordinate system, and if you remember, this coincides with the internal coordinate system of the CAD model of the gripper. So relative to its current pose, I can set the 3 position and the 3 orientation parameters here. So let's start with the rotation around the y-axis, so the angle beta. So here we can set the granularity of the rotation. We don't want to turn by 90 degrees, but rather in 1 degree steps. You see when I let go of the slider that the change is always relative to the last pose. So it is indeed really similar to jogging a robot in its tool coordinate system. So now we approximately parallel to the principal axis of the screw. So let's move up a little bit. So up is in negative Z direction, so I'm pulling the slider left, 10 1mm steps, once again. So I get just a little bit above the axis with the fingertips. Now another relative motion in the negative X direction, approximately 1 centimeter, so that the disc here lands just right in the middle of the 2 fingers. No need to hit that spot with 100% accuracy, as the gripper will center the piece when it closes. And click Apply to store the grip. Now let's open up the 3D Viewer app again under the IP of the edge device and initially arm the product. So for that, click on Products and select our screw. Then trigger the image acquisition by pressing on the yellow camera button down here. Acquisition is running. Just a few seconds later, we'll see a visualization of the recorded point cloud together with a visualization of the detected objects. The detected objects are shown in blue, and here in yellow we see a visualization of the gripper, respectively the pose that we will return to the robot for picking. And whenever the yellow visualization is missing, that means that we did detect the object itself, but the final gripping pose was rejected by the collision avoidance algorithm. So let's move on to the robot controller. In particular, let's have a look at the installation tab. And what I want to show you is that I already created a TCP for our gripper. And let's do a quick recap of the tutorial on training where I showed you how to prepare and upload the CAD model of the gripper. Here, the origin of the TCP coordinate system sits right in between the 2 fingertips. So relative to the flange coordinate system, we only have an offset here in Z direction. So let's use the gripper model to measure that offset. But of course, I could also look that up in the specifications of the gripper. But this way we find that the offset is approximately 171 millimeters. That's the value that I've already entered here. The standard approach to test whether we've entered the TCP data correctly is to take the robot and rotate it around one of the axes of its TCP coordinate system. So here we choose the x-axis, so the robot should turn around the axis that connects the two fingertips with each other. And luckily, that's exactly what's happening here. Let's put it back into its original position and switch again to the Installation tab. And here I wanted to show you two more things. First of all, that I've created a basis or a user frame. User frames and bases, they're called features here on the UR controller. Here, for example, we see the robot or world coordinate system or frame. The world frame is predefined, but I created a custom base which are called capture pose. This base or point feature describes the pose that the camera assumes for acquisition relative to the world frame. All the poses that we will later return from the vision system to the robot controller will be expressed relative to this basis. And secondly, I created a variable here called hand-eye calip. It's of data type pose. And as you can see, the value of this variable is already filled out. So for now, don't worry about where these values come from. We will later show you how to obtain them in the tutorial on hand-eye calibration. As you may have seen in our tutorial setup, the camera is mounted on the robot. So strictly speaking, it's a tool. And this variable describes the transformation of the tool or camera coordinate system relative to the flange. And what the relationship is between this tool and the base capture pose that we've created, I will show you at the end of the robot program. So here's the boilerplate code that I created. But before I dive deeper into the single steps, I want to recall the basic idea of our offering. And that is that through the API, we provide you with a toolbox of functions and services that are executed on the edge device, but can be called from any type of robot controller through the network. And before you start programming your robot, I would encourage you to have a look at our online documentation where you find a detailed list of all supported functions. As I just mentioned, functions are called by making requests over the network, and obviously, each type of robot will use a specific protocol to do so. Universal Robots Controller provide a client for communication with a so-called XML RPC protocol. And to such a client must belong a server that understands that same protocol. And that's why you need to make sure that our UR connector app is installed on the edge device. So we begin by initializing the client in the before start sequence. Access to the client interface is only available through UR script. That means we have to put the initialization command into a script block, and you'll find that block under the Advanced tab on the left-hand side. For further information, please also consult the freely available documentation of UR script. It explains in detail how to create the client by making a call to the function RPC factory. The first argument to that function is the name of the protocol, and we'll always keep XML RPC here. The second argument is the URL of the server, and of course, it must contain the IP of the edge device within the machine network as we've set it up in the tutorial on networking. For optimal precision, we recommend recalibrating the camera before every program execution. And that's easily done with the help of the function getProjectionMatrix, which we can call on the client object using the dot notation. The first, a tiny bit cryptic-looking argument here is the ID of the product which we've created in the previous tutorials, and we need to pass this here as the camera, and thus the parameters we want to calibrate here are attached to the product. You can easily get that ID by logging into the front end, visiting the product page, and then clicking on the yellow button next to the product name. This will copy the ID into the clipboard. But if you've got nowhere to paste it, then you'll also find the ID in clear text here above in the URL of the product. We will also pass that product ID to the function that is called in the next line. And the name of that function, a load configuration, makes pretty obvious what it does. It will make sure that all the parameters and configurations relevant to the recognition of the product are armed on the edge device at runtime. The function has a second argument, which is intended for the case where you run multiple apps or services on the device in parallel, and it ensures that the ARM request is directed to the right instance. Here we're using the routing key of the plane picking app. Should you be using some other service or application for inference, then please consult the documentation for the corresponding value. Now let's move on to the main part of the motion program. And first, as already stated here in the comment, we must move the robot into the capture position. Now recall the bases capture pose that I initially created and then the TCP of the camera that I put into the variable hand-eye calip. So I take that TCP and I move it to the base, which I can also understand as a desired pose of the robot relative to the world coordinate system. And when that motion is complete, the TCP will perfectly coincide with the bases. This will turn out very useful when we later drive the robot into the pick position. All pick positions are expressed relative to the camera coordinate system, and since we just make sure that the camera coordinate system coincides with the spaces, we can execute all the pick motions relative to the spaces. It's pretty clear what the next command here does. It triggers image acquisition and processing starts as soon as the image is recorded. This function, again, has two arguments. The first one, again, is used for routing. So in the case I'm running multiple apps, this keyword selects the one that I want to use for inference. The second argument indicates whether the function should block until image acquisition is complete. This is particularly relevant for the present case where the camera is mounted on the robot, where during image acquisition, of course, the robot has to remain static. But in case the camera is rigidly mounted inside the robot cell, I can set this argument to false, and this function will return immediately, allow me to execute motion commands while the image capture is in progress, possibly saving valuable cycle time. In either case, once image acquisition is complete, processing will start immediately on the edge device. But the control flow returns from this function and the robot program proceeds with the next command. In the meantime, the inference service puts all the computed pick poses on a priority queue. And what we do here is get the next best pose from this queue by calling the function getPose. The first argument, as usual, indicates the app from which the poses should be picked up. The second argument tells the API in which kind of representation the orientation should be returned to the robot. Here in your script, a so-called Eulerian representation of rotation matrices is used. But please check the documentation for what other representations are available on controllers of other robot vendors. The third argument is a Boolean flag that indicates whether the orientation should be returned in degrees or in radians, as here in your script. And the last argument defines the max waiting time in seconds. The thing is, this function returns a detection if it was already available when this function was called, or when a new result lands on the queue after the function was called. But at most, as long as we specify here in the last argument, in this case, 10 seconds. The return type of this function is an array whose first 6 elements contain the desired pose, or rather a prepose, as we will see shortly. The length of the array is actually greater than 6. For the meaning of the remaining elements, please consult our documentation. The only thing I want to point out here is that in case the getPose function times out, so no detection could be found in the maximal waiting time, the 7th and 8th element of the array are set to -1. So in a production application, of course, we need to handle this exception, but for the sake of simplicity, let's omit that today. Before we can use the pose data in a motion command, we need to cast it into a variable of type pose. And this variable I've also pre-created here in the installation section under the name preposition, and it has got the right type as indicated by the letter P and the 2 square brackets. The motivation to predefine this variable is simple. First of all, we want to be able to override it here from script. And second of all, we want to be able to use it later on in a simple linear motion block. Now we're finally in the position to make the robot move its TCP coordinate system into the pose defined by this variable. And as you can see, the robot is not assuming the final grip position that we've defined in the front end, but rather a so-called preposition, which we compute from the final position by moving it backwards in negative z direction by 50 millimeters. So let's have a quick look at the parameters of the motion block. So the frame of reference, of course, is the base capture pose that we've created in the beginning of the tutorial. And as tool, we select gripper, for which we've also created the TCP in the beginning. And last but not least, the waypoint comes from the variable preposition, which we set earlier in your script after retrieving it from the vision system. It's easy to see that using such a preposition is crucial. Imagine a situation where the robot is positioned right above a box, but also transversely displaced. If it was now attempting to take a linear path to the final pick position at the center of the bottom of the box, it's obvious that it would collide with one of the walls of the box. Starting the final picking motion from the preposition ensures that the robot is on a collision-free path. So the only thing that's left to do is move forward from the preposition by 50 millimeters. I can use a blocked linear motion for that, again with a tool gripper, but this time relative to the current TCP coordinate system. How the waypoint should look relative to the tool coordinate system is also pretty obvious. Let's briefly check by clicking on Edit Pose. Of course, we also select as View the current tool frame. And what we find is that indeed we're moving by 50 millimeters in the direction of the gripper Z-axis to compensate for the preposition. Now it's finally time to activate your gripper. How this can be done, of course, depends on the type of gripper and its software. So I think I'm ready to hand over at this point, but I'll close by recommending having a look at the tutorial on hand-eye calibration.